Welcome back to part 2 of circular motion. We're going to solve some problems in this section, so here we go. What I'm going to do is show you the problems we're going to be working on. I want you to pause the video after you've seen them all, and then I want you to try to solve them first before you look at my explanations. And this is our last one. All right, now that you've had a chance to work these out on your own, let's go through and work them out together. So our first problem says we have a car on an oval track. It's at rest at point R, so its velocity 0 right here, and then it moves counterclockwise around the track. It increases its speed at a constant rate until it reaches T, and then it travels at a constant rate until we get to point R, back around the track. So it's right here, so it begins at rest, and then it has a velocity to the right. So first things first, velocity is always tangent to the path. So it starts with a velocity of 0 here, and then the velocity is to the right, and then it is tangent to the path here, and here, and here. I guess this one should really be, because it hasn't quite gotten to the turn, it's just beginning, so the velocity should be right there, and then the velocity's this way, and the velocity's this way. So that's the way our arrows should point. So we've got to the right at S, and then at U it's down, and then V, and then W, and then X for our velocity. Piece of cake. All right, what about acceleration? So for acceleration, what we have is, remember that when we're speeding up, we're accelerating in the direction we're going. When we're slowing down, we're accelerating in the opposite direction we're going. And when we're turning, we are accelerating toward the center of the arc. So for this beginning part right here, we are accelerating to the right. So we have an acceleration. Let me put that in a different color so we don't confuse it. So here we go, acceleration and acceleration. And these are tangential accelerations because we're accelerating and speeding up. Now, around the turn here, we're accelerating towards the center because we're going at constant speed the rest of the way. So we have a centripetal acceleration towards the center at all times. Going around the turn. Here, we don't have an acceleration. The acceleration is 0 because we are not accelerating. Constant speed and not turning. And then here we're accelerating towards the center again. So let's see. At S, we're to the right. At U, we're to the left. At V, we're up and to the right. At W, we have 0. And then at X, we're to the right. There we go. That's our first one. Now our second one says we have a mass that moves in a curved path from point X to point Y. Which of the following diagrams indicates the possible combination of the net force on the mass, the velocity, and the acceleration? All right, so let's take a look at velocity first because it has to be parallel to the path. So you see right here, this velocity is not parallel to the path. So this one is right out. It should have been this way. So that one's gone. This one is the same. So this one is also right out. Okay, this velocity is parallel to the path, kind of parallel to the path, maybe. Okay, so now our second thing is that the force, the sum of the force, or the net force, force net, has to be in the same direction as the acceleration. Okay, so if this is to the right, that's to the right. Do we have any of those that are incorrect? Uh-oh, we got blurry. Here we go. So if we look at it right here, force and acceleration are not in the same direction, so this can't be right. Okay, force and acceleration in the same direction. Hey, this isn't right. Force and velocity are in the same direction, so that can't be right. So our answer is D. Okay, so let's take a little closer look at this. Notice that we have part of our acceleration is in the direction we're going, and part of it is perpendicular. So this is our centripetal part, which is making us turn. That makes sense. It's towards the center of the arc. And then we have a part this way. That's our tangential acceleration. That's the part that's making us speed up. So this object must be speeding up and turning at the same time. Okay, let's go on to our last one on this page. Skateboarder is skating over a circular bump. At the instant shown, she's at the top of the bump and moving with a speed of 5 meters per second. So that is to the right with a velocity of 5 meters per second. Is the normal force exerted on the skateboarder by the bump greater than, less than, or equal? Okay, so let's draw a free body diagram for a skateboarder. Here's our skateboarder right there. And there is a gravity force down and a normal force up. And we would usually draw them like this, but that would be incorrect this time. Because the skateboarder is going around an arc, there must be an acceleration towards the center. That means we have to have a larger force downward. So that means gravity force must be bigger than the normal force up, so that we have a net centripetal force downward, which would be mg minus Fn. That's our centripetal force downward. So the answer would be the normal force on the skateboarder is less than that of the weight of the skateboarder. In our next example, we have a child swinging back and forth, and we have one of these conflicting contention questions. And so I always tell students that what you need to do is need to highlight the stuff or box in the stuff that's correct and cross out the things that are incorrect. So let's take a look at Aaliyah's argument. At the bottom of the swing, she is moving exactly horizontally. Well, that looks good. Let me highlight that as correct. And then since she is moving vertically at that, or not moving vertically at that instant, the vertical forces cancel. Okay, that's incorrect because the person here is moving through an arc, so there must be a net force upward. So Aaliyah cannot be correct, so we cross her off. Brian says, just looking at the velocity vectors, the change in velocity points upward between A and B. Well, that has to be true because we're accelerating upward. So that is the direction of the acceleration. That's also true. And also the net force. That is also true. To get a net force pointing upward, the tension would have to be greater than the weight. All right, Brian, you're looking good. We like Brian's argument. So now let's take a look at Clara's argument. Clara says, but there aren't just two forces acting on her at the bottom of the swing. Well, let's check that. At the bottom of the swing, we would get something like this. We would have their weight downward. We would have their tension force upward, which we know from Brian has to be bigger than the gravity force. And, well, Clara, what's the third force? And let's see what she says. So she's moving in a circle. There has to be a centripetal force. Okay, there is no magical extra centripetal force. Never draw a centripetal force vector on your free body diagram because it's not a real force. Our centripetal force in this particular problem is the tension upwards minus mg. That's our centripetal force. Okay? Let's move on. Next example. A block is placed on a rotating disc that moves in a circular path. The discs have the same rotation rate in each case. Okay, what does that mean? Same rotation rate. Okay, that means that they have the same rotation rate, same omega. So they're rotating around at the same exact rate. That means they all make one revolution the same amount of time. But the masses of the blocks and the distance there from the center varies. All right, rank the magnitude of the frictional force on the blocks by the discs. Okay, so I'm going to draw a free body diagram. If we look at it from the top, we would see, so top view, we would see only the frictional force pulling to the left. If we look at it from the back, we would see a gravity force down, we would see a normal force up. These two have to cancel because the block is not accelerating up or down. And then we would have our friction force to the left. Okay? Now, we're assuming it's not sliding, so this would be static friction. All right, so now let's take a look at this. Our centripetal force is friction. So the sum of the forces towards the center equals MAC. So that's the friction force, static, equals M. And remember, our centripetal acceleration is v squared over r, but we don't know v. These these all have a different velocity if they have a different radius because they're going around with the same omega. So let's take a little side trip here and derive this. So we know that velocity equals omega times r, our tangential velocity from rotational motion. And if centripetal acceleration is v squared over r, and that's the tangential velocity, then if we put this in, we get omega squared over r. One of these r's cancels, and we're left with omega squared r. So I can take this and plug it in place of v squared over r, and that's our centripetal acceleration. So force friction static equals m omega squared r. So wait a minute. This is the same in each case. So the force friction static would be equal to, it would be proportional to m times r. So whichever one of these has the greatest m times r value, it'll have to have the greatest frictional force because the omega is the same for each one. So let's take a look. This is 6 times 2, so that's 12. That's 3 times 4, that's 12. 5 times 1 is 5. 2 times 5 is 10. So our ranking would be A equals B, and then D, and then, oh, not 5. What the heck? C. All right? Let's move on to our next example. So we have a ball that has a weight of 2 newtons. So that means mg equals 2 newtons, or if you prefer, force of gravity. And it's attached to the end of a cord of length 2 meters. So the radius of this thing right here is 2 meters. And it's being whirled around in a vertical circle, counterclockwise. So it's going around like this. The tension in the cord at the top is 7 newtons, and at the bottom it's 15 newtons. Speed of the ball is not the same at both points. Well, it shouldn't be, because it should slow down on its way up and speed up on its way down. It should be going fastest at the bottom. So remember that from conservation of energy, right? When it goes up, it has to slow down. When it comes down, it has to speed up. So what's our question? 3 students discuss the net force at the top. So let's look at the top. We have a gravity force down of 2 newtons. We have a tension force of 7 newtons. So we have a net force of 9 newtons down at the top. So let's see. Angelica says the net force on the ball at the top is 7 newtons. Well, that can't be right. Bo says the net force on the ball is 9 newtons. Both the tension and the weight are acting downward, so we have to add them. That sounds good. We like you, Bo. And Charles says, no, you're both wrong. We need to figure out what the centripetal force is. Whoa, boo. Okay, this 2 newtons down plus 7 newtons down is mv squared over r. That is our centripetal force. Those are the forces acting towards the center. So that's our centripetal force. So Bo is the winner. So now let's look at part B. Now the students discuss the net force on the ball at the bottom. All right, let's go back. We have a weight force down 2 newtons. And we have a tension, it says, of 15 newtons upward. 15 newtons. Okay, think about it for a second. Why did the tension go up? Hey, this ball still has to go in a circle, right? So there has to be a net force towards the center. So here the tension and gravity work together to make it go around the circle, so it's easier on the string. At the bottom, the string has to fight gravity, has to give it at least 2 newtons or otherwise it will fall, and then has to give it more to make it go upward in a circle. That's why the tension's greater at the bottom. All right, let's see what the students have to say. The net force on the ball at the bottom is 15 newtons. All right, Angelica, we're not doing so good today. How about Bo? The net force on the ball at the bottom is 17 newtons since oh, Bo, you were doing so good before. No, Bo, they're not the same direction. Charles, can you save us? The net force on the ball at the bottom is 13. I agree that you need to take into account both the weight and the tension, but they are in different directions, so they must subtract. Hey, way to go, Charles. Charles pulls it out of the fire and is the winner because 15 minus 2, that's our centripetal force. 15 towards the center minus 2 away from the center equals mv squared over r. There we go. Our next example is a conceptual question. It says a compressed spring mounted on a disc can project a small ball when the disc is not rotating as shown in the top view above, actually to the right. The ball moves radially outward. Okay, so here we are. It's sitting still, and this little spring in here launches the ball outward. Excellent. The disc then rotates in a counterclockwise direction as seen from above, and the ball is projected outward at the instant the disc is in the position shown. Which of the following best shows the subsequent path of the ball relative to the ground? Okay, so we're looking at it from above. The ball goes straight out, all right? Think about it. What happens when this thing is rotating and the ball is right here and it's rotating around, omega? What's the velocity of the ball then? The velocity would be this way. So this is the velocity when it rotates. This is the velocity when it gets launched. If you do both at the same time, you get this. All right? Easy peasy. There is a tangential acceleration to the rotation, and then there's a launch velocity outward, and they add up to give us this velocity right here. Done. In this particular problem, we have a ball attached to a light string that's spinning around counterclockwise, and I've shown what the omega direction is then, as shown. Which of the following arrows represents one of the forces exerted on the ball at the moment it passes point P? So when the ball is right there. Let me put a different mark for that one. Here we go, when the ball is right here. Now it says select two answers. You must select two on the AP test and get them both right in order to earn points. So, well, we've been saying that when it goes around a circle, there has to be a force towards the center. So there has to be one to the left. Let's draw a free body diagram. What would be the forces on the ball here? There would be tension this way, and then there would be a gravity force down on the ball. So we would have D as our tension, and we would have C as our force of gravity. There we go. Don't be intimidated by these pick two questions. Most of the time, they're very straightforward, and you can eliminate the ones that can't be right. Like on this particular one, there is no way that there is a force upward on the ball, and there's no way that there's a force to the right pushing the ball outward. The string's pulling it in. So we're left with C and D. They have to be correct. Now, an extension of this problem is a yo-yo is spinning counterclockwise, just like above, in a vertical circle. Okay? When the yo-yo is halfway between its highest and lowest points as shown, what's the direction of the acceleration? Now, this is a decoy problem. Please be careful. We'd say, hey, it's going in a circle. The acceleration should be to the left. And you would be partially correct. There is indeed a centripetal acceleration towards the left because it is going in a circle. However, there is a force of gravity pulling it down. The ball is actually slowing down as well. So there is another type of acceleration here, a tangential acceleration this way, because we have a gravity force down and a tension to the left, which means that the net force is in this direction. So therefore the acceleration, F equals ma, must be in the same direction. You add these two up, you get an acceleration somewhere down to the left. Our answer is C. Our last question is a free response question. It says a physics student is at a state fair and boards a ride that's a big spinning cylinder, and the walls are made of rough rubber. You get in this big cylinder, it starts to spin around, and you stick to the wall. The floor is initially there under your feet, and then the floor drops out, but you're stuck to the wall, and you stay there as long as it's spinning. Okay, the dot represents this student right here. Draw an accurate force diagram showing and labeling the forces. Accurate. That means they want you to make sure that you draw them to the correct appropriate lengths or proportional lengths. So what's that mean? First of all, remember you always draw the forces and not components. Second thing is when they have a grid like this, always draw your arrows to the grid. So like I know there's gravity down, so I'm going to draw one down like this, and I'm going to draw it to this line right here. Always draw it exactly to one of these lines. Don't leave it up to interpretation for the reader. The lines are there for the reader to help them understand what you mean. So use the lines. So this is my force of gravity. Also, make sure that you label it. If you don't label it, you can't get credit. The free body diagrams are easy points. Don't throw them away. There has to be a force towards the center. Their back is against the wall. What's the length of this one? I actually don't have any idea. Could be larger or smaller than this one, but I'm just drawing it to this mark right here. What's more important is what's the force holding you up so you don't slide down the wall, and that is friction. Now if I draw that one, I need to draw it so that it cancels this one because we're not accelerating up or down. We're only accelerating towards the center in this circular path. So this is my force friction, and it's static, and it's the same size. So I mark this one to the third line as well. You can even, for safety purposes, do this to tell them that they are the same, just to help the reader out. Now, an adult with twice the mass of the student is also on the ride. They remain stuck to the wall while the ride is rotating just like the student. Derive an algebraic expression to show that the mass of the rider does not determine if the rider will remain stationary against the wall while the ride is rotating. Okay, this is a QQT type problem, a qualitative quantitative transition problem, where they ask you some qualitative questions that do not involve any kind of math, and then some quantitative that involve math. Notice that this math is symbolic in nature. That's typical. So get used to deriving equations. So how do we go about solving this particular problem? Well, let's write down what we know. We know that in the x direction, we're accelerating towards the center. And in the y direction, we know that the forces have to cancel out. These two cancel because we're not accelerating up or down. Okay, so let's plug in the variables. So our force towards the center is the normal force. That equals mv squared over r. In the y direction, we know that the force friction static must equal the force of gravity. And we know that the force of gravity is equal to mu force normal, and that equals mg. Now, we have to be a little bit careful here. Those of you at home may be saying, hey, wait a minute, force friction static is less than or equal to mu force normal when this is the static coefficient of friction. You're absolutely right. But we're talking about them, the person not sliding down the wall. So we're at that maximum amount of friction where we're just at the point where we're not sliding. Okay, so I'm just going to put it in as equal because we're at the maximum value. All right, well, there's force normal, so I can plug this in over here and I get mu static, m v squared over r equals mg, and voila, the mass cancels out. So the mass doesn't matter. So a heavy person, light person, a tiny child could all ride this ride and not slide down on the wall and would work perfectly. And that's it. Those are our examples for circular motion. Our next video is going to include circular motion problems where gravity is the force towards the center. We end up with a few unique things about that, so I'm going to put that in a separate video. Until then, see ya. Bye.